All right, take it away.
All right, well, hello friends. As you know, my name is Lydia. The project I've been working on is developing a CD microfluidics device to capture and isolate cancer stem cells. For Colin and Terry, this may be a little repetitive or review because you all know what the progress I made. For you guys who don't know my project, I'll talk about a little bit the background behind it as well as the work I've done. So, for those of you who haven't heard my presentation, a little introduction about cancer stem cells. Cancer stem cells are like regular cancer cells in that they have the ability to self-renew, differentiate, and grow rapidly. However, cancer stem cells also have the ability to form tumors, and that's kind of one of the reasons why cancer persists in an individual's body, and one of the reasons for relapse and metastasis. Currently, the conventional cancer therapies that are out there do not target these cancer cells, so that's the reason for tumor relapse, as we can see in this diagram on the bottom. However, if we're able to create treatments around cancer stem cells, we can eliminate these cancer stem cells from the tumors, and it will lead to tumor regression. So another differentiating factor between cancer stem cells and non-tumorigenic cells is that cancer stem cells have a higher cell membrane capacitance. So we're going to use this property to our advantage in this project. So some of the goals we were trying to achieve was ultimately, as the title says, to capture and isolate cancer stem cells using a CD microfluidic device. More specifically, the goals were to separate about 90% of the cancer stem cells using a phenomenon called dielectrophoresis, or DEP, which I'll discuss a little later. We also wanted to separate the cells based on a temporal separation. So based on time, we want to see if we could separate the cancer stem cells versus non-tumorigenic cells. And we had a few design ideas, and between the design ideas, we wanted to determine which one would be the best. So why is this device important, and why is research important? Ultimately, it's going to serve as a research tool so that scientists focusing on cancer research or pharmaceutical companies developing cancer treatments can understand cancer stem cells more in depth in order to develop treatments that can target them at its core. So here were some of the design ideas we were planning on doing. So this image over here shows a very simple SolidWorks model of how the device should look. The base is a glass slide, and on top of it is patterned gold electrodes in the form of interdigited electrode arrays. And then the next two layers they compose of the channels and the adhesive. So for the channels, we had two design ideas. One was PDMS, the other one was CNC machine plastic. We wanted to determine which design the fluid would be able to flow through easily and to promote separation. For the CNC machine plastic, the adhesive layer would be pressure-sensitive adhesive, some sort of tape. And then for PDMS, we would use a thinner layer of PDMS. So DEP, it stands for dielectrophoresis. And dielectrophoresis is a phenomenon in which a non-uniform electric field is created, and that directs the movement of electrically polarized particles, and it promotes the separation of the cancer stem cells versus the non-tumorigenic cells. Again, that's based on the differences in their cell membrane capacitance. And we wanted to see which of our, now we have the two different IDA, interdigital electrode designs, rectangular and trapezoidal, and between the two, we also wanted to see which one would provide for a high sensitivity, as well as which would promote for a better separation. So ultimately, we want to eventually be able to separate them based on temporal separation. So separating them based on time. So first, because the cancer stem cells are going to be more affected by the electric field, the non-uniform electric field, they'll go slower. So first, the other cells and cancer cells would be flushed through the channels, and then after some time, we will collect the cancer stem cells. Some of the current work, so earlier this year, we wanted to sample dielectrophoresis on a sample device. So we did that. We were able to see separation of polystyrene beads. And the reason why we use polystyrene beads is because it imitates the behavior we expect to observe with cancer stem cells. We also tested plasma bonding, which is the way we can attach the two layers of PDMS together to see whether fluid will run through and not provide any leakages. So we were able to successfully do that, and we also designed the two different types of electrodes. So we conducted a few tests this quarter, and what we observed is that at low frequencies and high voltages, what is hydrolysis occurred, so the breaking of hydrogen bonds. And what happened with that is that it formed bubbles, and it obstructed the view of the electrodes, but it also destroyed our devices. So we needed to find what is the optimum frequency and voltage ranges, our DEP parameters, where we can prevent hydrolysis from occurring, but also see a good separation of the beads. So what we found out is that there was a higher sensitivity for the rectangular electrode shapes compared to the trapezoidal shapes. Okay, so see that image is hydrolysis. I thought I put a picture here that shows the separation, but however, we were able to see a very distinct separation of the polystyrene beads. And what we observed is what's called negative dielectrophoresis, or negative DEP, where we observe the beads move towards the center of the electrodes, towards the field where it's less, the strength of electric field is not as high. So that's kind of what we observed. Right now we are still trying to test to see if we can find a crossover frequency where it changes between a negative dielectrophoresis and positive. So between or opposite, between whether it moves between a high electric field or a low electric field, and this will enable us to count the count the particles better. So, and we're still trying to find this is the range. So for the trapezoidal, we found that the frequency of around 2500 hertz worked very well with a peak-to-peak voltage of around 6 volts. For the rectangular, it's more sensitive, so 15.3 kilohertz. No, yes. And peak-to-peak voltage of. So right now it was mostly just trying to find the optimum DEP parameters, which we could observe a good separation of polystyrene beads. Actually, next week we're testing with HeLa cells, which are cancer cells, to see if it will work and maybe tweak the parameters a little bit to fit with cancer cells. So that's the plan for next week, and after that, if we find an optimum DEP parameter, the next step would be to create channels, so creating the PDMS and CNC machine plastic channels, but also adding a CD component. The reason why we add a CD component is because it provides a centrifugal force, and that will be able to separate these cells based on their densities, so initially. And yeah, so this is actually what we are going to be doing. And this image here shows how the base looks like with the interdigital electrodes. So there are already some devices that use electrophoresis to separate particles and cells. But what makes this project a little bit different is that we are trying to add a CD component. Again, that's to initially separate the cells more efficiently and to separate them better. And we're also testing dielectrophoresis with different shaped electrodes and seeing what differences in results can we get, which we've observed that the rectangular is more sensitive. And again, we also, in comparison to the other research that's out there, we'd like to achieve a higher degree of separation. Things that I've learned, I learned a lot about dielectrophoresis, so learning about DEP is an entirely new concept for me, so now I feel like I learned a lot because that's pretty much what the device uses. Also different kind of fabrication techniques that we have to do in order to construct this device. And overall, just learning about cancer stem cells, this is not really a field that I've learned too much in my courses, so I had to do a lot of extra research on my own and learned a lot about how cancer stem cells work, differentiating factors between regular cancer cells, as well as other cells. So that is my presentation. Thank you.